I would like to remind you that for more Microsoft webcasts, you can go to microsoft.com/webcasts. Thanks again for joining us for today's presentation, SQL Server 2008, Part 2 of 3, Manage Large-Scale Data Warehousing. Now it is my pleasure to introduce today's presenter, Eric Hanson. Eric, you now have the floor.
All right, thank you, Alex. So I'm Eric Hanson. I'm the lead program manager for query processing in the SQL Server Engine team, and I've been coordinating a bunch of our activities associated with data warehousing for the SQL Server 2008 release. And so today I'm going to talk about what you can do to effectively manage your large-scale data warehouse. Here's an overview of the agenda. The main points I'm going to touch on are related to the overall data warehouse architecture, how to do hardware and capacity planning for your data warehouse, database and storage design, both logical and physical database design for a data warehouse, good practices for your extract, transform, and load processes, or ETL processes, how to manage your data, your large tables based on partitioning, how to effectively manage resources in your server using our new resource governor feature. Talk a little bit about high availability techniques that are associated with data warehousing, and a little bit about performance monitoring and troubleshooting, and then take a couple questions. So here is a diagram of a typical data warehouse architecture based on the Microsoft tool set. You'll see that at the bottom we have our data sources. We migrate data from those data sources into staging databases or an operational data store, sometimes called an ODS. From there we load the data into our dimension tables and fact tables, which make up the relational data warehouse. Typically, we also have analysis services cubes, which we build off of the relational data warehouse to facilitate high-performance reporting and a better semantic understanding of the data based on a star schema model and dimension hierarchies that are explicitly represented in metadata and analysis services. So that part in the middle is the relational data warehouse. Next, let's talk about how to plan for hardware and figure out how much capacity you need for a data warehouse workload. Just a few words about hardware. As you all know, 64-bit hardware is becoming prevalent now. That basically all new processors that you buy for PCs and servers are 64-bit. This is very useful for data warehousing because 64-bit machines can have a very large virtual address space, and very large buffer pools, which are useful for caching large pieces of the database in memory, and also lets you do large-scale operations like large hash joins and index builds with minimal I/O, so it really speeds up performance for data warehouse. How many processors do you need? So anyway, use a 64-bit processor or a suite of processors for your data warehouse, and buy as much memory as you can afford. As far as processes are concerned, a lot of data warehouse queries are CPU bound. That means the CPU resources are the limiting factor in determining how fast those queries run. So again, buy as many as you can afford. The typical query processing rate for SQL Server, the slide is not quite right here. I did some more analysis. It's actually 2 million rows per second per core to sequentially scan a table and join it to a set of dimension tables and then do grouping and aggregation, which is what a typical star join query does. So you can use that number, 2 million rows per second per core, to sort of get a ballpark estimate for the upper bound and query processing time for a well-written star join query. As far as memory is concerned, you should have enough main memory available to get the 20% of the data in your database that's most frequently used into your main memory buffer pool, so it's cached in memory all the time. For example, Now let's consider a modern piece of hardware. Suppose you had a 4-processor computer, quad-core processor, so you got 16 cores. You can buy that for about $45,000 with 128 gigabytes of RAM, not including the I/O system, maybe even less than that at this point in time. 20% of, if you compress a 1 terabyte data warehouse, it'll be about 300 gigabytes. And then 20% of that is less than 128 gigs. So, if a 1 terabyte data warehouse compressed, 20% of the most frequently used data will fit in memory on a machine like I just described there. And that'll give you a very, very high buffer hit rate so that almost all of your queries are operating out of main memory, so you're not constrained by the disk I/O bandwidth. Equally as important to the CPU and memory resources that you have for your data warehouse is the hardware that you have for your storage system. A rule of thumb is, if you remember anything from this slide, just remember this. Designed to have 250 megabytes per second of sequential read I/O performance per core. So one core can process about 250 megabytes of data in the buffer pool per second. So having an I/O bandwidth of 250 megabytes per second per core will balance with that, so that you won't have queries be I/O bound or CPU bound. You want it to be balanced. Now, a single disk can deliver roughly 50 megabytes per second, depending on the type of disk. But so that's 5 disks to keep one core busy. So it takes a lot of I/O bandwidth to saturate the capability of a single commodity shared memory multiprocessor server, like a 16-core server like I just described. You can use measurement tools like SQL.io.exe or IOmeter.exe to measure the effective I/O performance of your system. And so we recommend that you use these tools to verify that your I/O system is delivering something like 250 megabytes per second per core for most efficient and balanced performance. Most large enterprise data warehouses do use a storage area network, a dedicated SAN. There's no one right way to do it. A lot of customers do prefer using SANs because they allow you to do certain management operations more easily. Like, for example, you can do backups using a SAN snapshot, or you can take a snapshot of the data to do testing or development. You can take a snapshot of a production database and do that. You should always separate your log from your data to keep it on separate LUNs or spindles. So I'm not going to go through all the points here, but these are some of the main points that you should remember for designing a good storage system for your data warehouse. During the SQL Server 2008 development, we were using an HP Integrity Superdome computer, which was provided by Hewlett-Packard, so we could test SQL Server 2008 at very high scale to make sure that we could get full power out of the machine and that we could speed up query processing as well as possible on this type of machine. So here's a picture of one. Actually, it's the one we used, and just to give you an idea about the capacity of this machine, it was split into actually 3 different hardware partitions, one of which is called AS Dune, was used for relational data warehousing, and it had 32 cores and 128 gigabytes of memory, and its sequential read performance underneath all those 32 cores was 4.1 gigabytes per second, or 4,100 megabytes per second. That's a little less than the I/O capacity I recommended, but with today's modern processors, again, 250 megabytes per second roughly is a good number. To sort of spark your interest in SQL Server 2008, I wanted to quantify some of the improvements we got compared with SQL Server 2005 for query processing on this 32-core machine. Again, this is a little bit of a detour from managing your data warehouse, but it's an important data point about SQL Server 2008 for you to consider. We developed an internal database and benchmark workload on a 6 terabyte database with 25 billion rows in the largest fact table. And we had 123 queries which we assembled as part of this internal benchmark. We divided the queries up into 5 different groups. We ran the benchmark on both SQL Server 2005 Service Pack 2 and on SQL Server 2008. And so we divided into groups based on group 1 through 5, where 1 is the fastest group of queries and 5 is the slowest on SQL Server 2005 Service Pack 2. And we kept the groups fixed, ran the same queries on SQL Server 2008, and we got some very interesting speed-up data. So the speed-up is represented by the ratio of runtime of the old version of the query on SQL Server 2005 divided by the runtime of the new version. So, for example, 200% would mean the query was twice as fast. So overall, we have a geometric mean speed up of 254%. And the median speed up is 175%. So that means the queries are average 75% faster. I shouldn't say average. The median query is 75% faster. So the geometric mean is quite a bit higher because some queries speed it up a whole lot, like a factor of 80. But the median queries were, just a little less than a factor of 2 faster. Also, if you look at the groups 1 through 5, the fastest queries didn't speed up as much because in SQL Server 2005 they already had very good query plans and very good performance. The sweet spot is sort of in the middle range. The queries that were running, maybe for 2 minutes in SQL Server 2005 are now running in more like 30 seconds on SQL Server 2008. So we got very impressive query speed up. The only thing we did here differently was to use compression. We call it page compression on the fact tables in SQL Server 2008. There were no other changes at all. There were no changes to the queries, no changes to the index or partitioning design. The sum of the total query runtime is about 60% of the total time for SQL Server 2008 compared with 2005. So very significant speed ups in SQL Server 2008. Let's talk a little bit about capacity planning. So the hardware vendors have some excellent advice available about capacity planning for certain different types of workloads like OLTP and data warehousing. For example, HP has these published reference configurations that you can utilize. They have a website with some tools that help you do capacity planning. It's called the Active Answers website. So also, before a big project, you might want to consider either using those kind of reference configurations, or you may even want to consider a trip to your hardware vendors or Microsoft's lab to test your workload on a large machine to help you do capacity planning. Again, 250 megabytes per second of I/O capacity is recommended. Storage capacity, a rule of thumb is to figure out how many bytes of data you need for your database. For example, you can find out what the size of a fact table is by the number of months of data, number of rows per month, row size in bytes, multiply those together and divide by your compression factor, and that's the size of data that will actually be stored in your fact table. You should reserve about 3 times that for headroom for growth of the data and reorganization, in case you need to build a new index or reorganize the data, or partition in a new way. CPU capacity planning is a little bit more complex. It is application dependent, but there are a few sort of techniques you can use are, basically it's based on a little common sense and high school algebra. So you can model your peak multi-user workload and to be able to satisfy that workload with a certain percentage of the CPU time to spare. You can measure the average CPU seconds per query and estimate the peak number of queries per hour, the CPU seconds you need per hour, and then you can figure out how many cores you need to satisfy that at a certain percentage of CPU utilization using formulas like I've shown here on the slide. If you want to be able to plan capacity to give you certain type of query response time, you may need more parallel capacity if you want the response time to be really fast. If you're worried about more than just multi-user throughput. So, as an example, again, as I said before, SQL Server 2008 can typically process about 2 million rows per second per core to do a star join query with grouping and aggregation. So you can look at the query time. Would be the query time is going to be rows touched by the query in the fact table divided by rows per second per core, which is 2 million, times the number of cores. So that's a very rough, sort of crude way to measure the response time of a star join query. So based on that, you can calculate how many cores you're going to need for a specific response time. So if you look below here, for example, if you have a fully parallelizable query and run it to run in 5 seconds maximum on the available cores standalone, and you're doing, say, so suppose you were doing 1 million rows per second per core for this, then you need 10 cores to do that based on that calculation. Now on 2 million rows per second, which is our real throughput, more likely, then you'd only need 5 cores. Also, think about other long-running operations besides just queries. For example, index build or index reorganization, or creation of summary aggregates, or database consistency checking, backups. You may need, you should measure the time it takes to do this on your database so that you can figure out what, and given the available batch window you have to do these operations, you can make sure you have enough capacity to perform these operations in the desired batch window. There are other things you can do to help reduce the total capacity that you actually need, like you can use partitioning to make it so that your index maintenance requirements are much smaller than they would have been otherwise. I want to say a few words about hardware tuning. Again, this is very machine specific, and you really should consult your hardware vendor to tune your hardware. But there are a few things associated with SQL Server performance that you should definitely take a look at and make sure that they're set properly. Your host bus adapters for your I/O system often have a queue depth setting. Normally this is set to 4, but for SQL Server data warehouse systems you should set it to no less than 32. And for fiber channel connections, use the maximum available setting, which is 254. Now I'm going to move on to talk about database design and storage design for an effective data warehouse installation. The logical data warehouse schema is very important of your overall data warehouse design. We recommend that you follow the dimensional modeling technique whenever possible. Well, the SQL Server system is, it doesn't require the use of any one modeling technique for data warehousing. We do a good job with dimensionally modeled data warehouses, as well as data warehouses which are normalized, like in third normal form. But we do recommend that you use dimensional modeling because this is a well accepted technique. It dovetails nicely with the modeling capabilities and analysis services, and you'll often be building analysis services cubes from your data warehouse. Also, it makes it easier to write relational queries using a star query pattern. There's some specific star query optimizations that are new in SQL Server 2008 that work really well on this type of schema. You should use integer-typed surrogate keys to link the fact table to the dimension table. So every row in the fact table should have a set of, that it will have a set of surrogate keys that reference dimension table rows, like the product key, customer key, and so on. The reason for this is it helps keep the fact table smaller by having small dimension keys in the fact table as references. It also compresses very well, and we have a new data compression feature that I mentioned. It also facilitates further optimizations during query processing. There are some algorithms in the query execution system in SQL Server that work best on integer types for join columns. You should avoid using primary key and foreign key constraints declared on the fact table. This saves CPU during your extract, transform, load process. Usually, if you declare a bunch of foreign key references from your fact table to the dimensions, yes, that is logically correct. However, it will add a lot of cost to your load process for your data warehouse. Also, you're usually doing this at the application level in your ETL process anyway, so it's kind of a wasted effort. Your large tables, your fact tables in your data warehouse, typically you'll want to partition those if they're bigger than a certain size. You do this to plan for a sliding window scenario. It's quite common that your fact tables in a data warehouse have a useful life of, say, maybe 3 to 5 years. Beyond that time, the data doesn't have as much business value anymore. So you may want to only keep around the most recent, say, 3 to 5 years worth of data. When the data ages beyond that window, you'll want to age it out. You want to remove it from your fact tables. Partitioning lets you do this very efficiently by swapping out the old partitions in a metadata-only operation. And then you can truncate the tables that you've swapped out. You'll be loading data into the newest partition only, typically, or maybe the newest 2 or 3 partitions if there's a few updates to some of the more recent data. If you have more than 50 gigabytes in a fact table, typically you should be partitioning that table. So again, partitioning is only needed for the fact table, not the dimensions. You should partition on the time key or date key, whatever you're calling it. This is the thing that it's a timestamp or foreign key that references a date dimension row. Pick a partitioning granularity like week or day. Remember that we have an upper limit of 1,000 partitions in SQL Server, so if you're going to keep more than a couple years of data, you want to be partitioning by, say, week or month, not by day. Otherwise, you'll run out of partitions. Remember to keep empty partitions at both ends of the table for efficient maintenance. And we'll talk about this a little bit more in a second. We fixed a number of issues with parallel query processing on partition tables in SQL Server 2008. So this is a query processing performance enhancement, not really a manageability enhancement, but realize now that you don't have to make your partitions narrower just to get more parallelism. Parallel query performance is more or less independent from your partition width now. And that was not the case in SQL Server 2005. Now, suppose that you want to load a very large partition table, do an initial load of that table. You have a multi-terabyte table and you want to load it for the first time. Here's a technique that can allow you to do that very quickly using partitioning. You create a partition table that has no indexes. Then you create non-indexed tables, one for each partition. I call these switch tables. Then you populate these, prepare them with the proper constraints and so forth. When they're all prepared, then you switch them all into the target partition table, so that you can load the individual switch tables in parallel separately. So we have demonstrations and examples where we are able to load a terabyte table in well under an hour. Let's say a few words about physical database design. So I already have talked about logical database design, designing your schema, and recommended you use a star schema. Physical database design refers to the physical file structures and indexes you use for that data. So good physical design is essential to get good query performance. And the ideal physical design depends on your query workload, depends on your maintenance window size, it depends on your overall performance expectations. But there are a few common requirements. We want to keep the size of the fact table reasonable to limit storage costs. That's related to, so we may not want to create too many indexes on the fact table. That'll make the fact table bigger. We also want to compress the fact table to make it smaller. We want to provide good access paths to dimension tables during ETL for slowly changing dimensions. So typically for the dimensions, you're going to want to have non-clustered indexes on the frequently filtered columns of those dimensions, and also have a clustered index on the natural key of the dimension table and a non-clustered index on the surrogate key of the dimension table. Another reason to use compression is to reduce I/O. So if you use page compression, typically your data will be about 1/3 of the original size. We've seen anywhere from a compression factor of 2 up to about 7. Using page compression, again, because it shrinks the fact table so much, if you compress it, you'll reduce the I/O requirements for query processing, and that will speed up your queries very significantly. One thing you should be aware of, however, that's related to managing your data warehouse is that when you build a clustered index, when you build a compressed index, it takes longer than building a non-compressed index. So when you're loading a table, for example, it takes about 2.5 times longer to load a table that's compressed compared to a table that is non-compressed. So that's something you'll have to factor into your ETL process design. More about fact table physical design. Build a clustered index on the date key. That's the surrogate key for date. Also, you should partition on the date key if the table is very large. It's larger than 50 gigabytes. And build non-clustered index on the frequently used foreign keys that are used for joining with dimensions. So for example, you might want to have a sales fact table that had a clustered index on date key, was partitioned on date key, and then had non-clustered indexes on, say, product key and customer key. That might be a reasonable physical design for a sales fact table. These non-clustered indexes support pinpoint queries that let you extract rows based on selective dimension conditions, let you do that very quickly. One final note is that the size of temp DB should be about the same as the size of the largest fact table. Continuing on physical fact table design, again, partition your large fact tables. You should use a meaningful date key of type integer, or I would recommend type integer, and use that 8-digit encoding with 4 digits for year, 2 digits per month, and 2 digits for the day. Don't use a meaningless surrogate key for date. You want the data to be ordered by date inside the fact table so that you can partition by the date key. Also, you want to enable your query developers to explicitly put range filters on date on the fact table so they don't have to imply a range filter via a join with the date dimension. That'll help their queries run a lot faster. I already talked about dimension table physical design, so I'm gonna skip this. A very important part of physical design is your choice of summary aggregates. One approach would be don't design any summary aggregates at all. Just all your queries go against the raw data, the fine-grained fact data. Another approach is to pre-materialize summary aggregates, so you're pre-materializing the results of a lot of queries this way. The most recommended way to do this is simply to use analysis services and to use the aggregate capability of analysis services. So if you build AF cubes off your relational data warehouse and then use the aggregate design tools in analysis services to design an effective set of aggregates, then most of your queries in analysis services will be processed using those aggregates rather than the raw data, and you'll get very, very fast query response time. Now, if you would like to do your reporting not on analysis services, but instead use SQL to do reporting on your relational database, and you have a large database, then you may want to consider using summary aggregates in the relational database itself. So what you can do is either use index views or user-defined summary or aggregate tables. Index views are a form of, you can use index views to create summary aggregates on fact and dimension tables joined together so that certain queries can be answered just using the index views, and they won't have to refer to the fact table at all in order to be processed. And since the index views can be much, much smaller than the fact table, this can be a huge performance boost. So, for example, if you were running a lot of reports that asked for total sales by product and store, you could create an index view that grouped by product and store and had the total sales for each store for each product. And the number of products times the number of stores may be far, far less than the total number of items in the fact table. An alternative is to use user-maintained aggregate tables, and then you can explicitly write your queries to target these user-maintained aggregate tables. Some users find this to be a very effective way to do things. It does come with a cost in terms of the complexity of writing and maintaining your reporting applications, because you have to explicitly name these different tables in your queries rather than naming the fact table. You can also explicitly reference index views by name using the no-expand query hint in SQL Server 2005 and 2008. This is a nice trick because it gives you similar benefits to using user-maintained aggregate tables, and that you can target a specific aggregate and know the query is going to use it. But at the same time, the system will automatically maintain the aggregate and make sure that it is correct and in sync with the raw data. Whereas with user-defined aggregate tables, you have to maintain them during your ETL process, and if there's any bugs or mistakes in that process, then you may get wrong results for some of your queries. So again, to recap, use analysis services cubes whenever possible for aggregates. Tweak your regular indexes to get good performance. If your performance is not satisfactory and for relational queries, use partition-aligned index views. You may use the no-expand hint for index views if you want to target them explicitly in your queries to make sure that you're using the index view. Only then would I use handwritten aggregate tables if that doesn't satisfy your needs. Now, I'm also going to say a few words about manual query tuning. Query tuning is sometimes thought of as a development task more than a system management task, but lots of production support DBAs end up having to tune some queries. If you see that a certain query is slowing down your system, you may need to come in and help rewrite the query or create an index or an aggregate or something to make the query faster. So again, manual query tuning is the last resort if everything else fails. Common steps in query tuning are check to make sure that you're doing partition elimination properly. You should place a where clause on the fact table directly that pulls out a specific range of values from the fact table, from between one date and another, for example. Now this is why the date key should be a meaningful key, as I spoke about earlier. So if you really need to tune a query, you should filter on date based on an explicit predicate on the fact table and not via a join with the date dimension. You can use hints if necessary, like index hints, join hints, or grouping hints in order to speed up a query. You can specify the order of joins using hints. One typical thing you may want to consider in a data warehouse query that uses star join, grouping, and aggregation, if you're not getting good performance, is try to modify your query so you have an explicit range predicate on the date key, and then if you're not getting a hash join in the query plan, use an option hash join hint to try to get a hash join. This will often result in better execution time. Another thing to consider is to pre-materialize partial intermediate results in temporary tables and then write an additional query or queries to assemble the final result. So we've seen some people really like to use common table expressions to create sort of temporary intermediate results because logically that's what it looks like in your query. However, sometimes that can confuse the query optimizer. So if you're having performance problems with a query like that, you should consider taking any small result set that would be derived from a common table expression, materializing that into a temp table, and then writing another query to finalize the computation. Also, it can also be improved performance to filter rows from a dimension table and put those in a temporary dimension table. Just a small set of rows from a one dimension table could be stored into like a temporary dimension, and then you could join that to the fact table and other dimensions to produce the final result. That can also help get a better query plan. So serious query tuning is an art. I just gave you a few ideas on how to do it. These are some initial things to consider. If the things I mentioned here so far don't work, then you might want to consider using summary aggregates like a user-defined summary table or an index view or analysis services to get things to go faster. Also consider your hardware. You could take a look at the I/O that your query is doing. If it's doing a lot of I/O, make sure that you have a fast enough I/O system, you have enough main memory for your computer, and you've got compression turned on, and so forth. If you look at this, here's an example of how to do range elimination in your queries. So if you look at the bottom, there's two selects. There's one that selects from a fact table called sales, where the date key is between one constant and another. And then there's the second query, which means more or less the same thing. It's selecting from the sales table where the sales are filtered by date key via a join with the period dimension. So both of those might really pull back the same exact rows from the sales fact table, but the first one has some advantages in that you can get a fully parallel scan working for that query more easily. So if you're having query performance problems and you're using explicit You're filtering by date via a join with the date dimension or period dimension. Then again, consider using an explicit filter where on the fact table where the date key is between one value and another. So as I mentioned before, partitioning is a very powerful tool for managing large data warehouses. And I'm going to illustrate how to load data and unload data from a partition fact table to implement what we call a sliding window scenario. So suppose that you want to load data into the most recent partition on a fact table. Suppose we got this existing fact table here, which has these 5 partitions, one empty partition at each end. And now we want to load into the newest partition, that empty partition. So let's see how that will look. What we do is create a staging table in the same file group as the target partition, which is number 5. Create that staging table. Then we're going to split the most recent partition, adding a boundary point. Okay. Now we'll now we'll bulk load and index that staging table, fill it up with data. Finally, we'll switch the data into the next to last partition, number 5. Okay? So now see we're left in the same state again. We've got an empty partition on each end and full partitions down the middle. One of the nice aspects of this was that we didn't have to drop and rebuild indexes on the fact table. All we did was work on a small chunk, that one partition, load it and build its indexes, and that was all fast. Now let's consider how to unload the oldest data from a partition table. So what we want to do is unload, we create an unload table in the same file group as the partition we're going to remove, which is partition number 2. So there's the unload table. It's now empty, but it has the correct schema that lines up with the schema of the fact table. It's on the correct file group, same file group as partition 2. We switch out the second partition. Bam. So that's a metadata-only operation. Happens very quickly. It takes sub-second time. Now we have 2 empty partitions at the end, so we need to clean things up. So let's merge those 2. And now we're left again with 1 empty partition, one at each end of the table. And now we can do whatever we need to with that old data. We can either archive it or truncate it, or both. Now let's take a look at best practices for extract, transform, load. One thing we should talk about with respect to incremental is incremental load. You want to avoid concurrent bulk insert into the same partition because this can cause concurrency problems and maybe deadlocks. If you need to load with concurrent queries, you can use bulk insert BCP or the SSIS OLADB destination and keep a small commit size. This prevents lock escalation. Avoid using the table lock hint because you want to be able to concurrently load it, with multiple jobs into the same table, and use multiple threads to load in parallel. An important part of managing your data warehouse is how do you load data and manage your statistics, and specifically how does loading interact with statistics. Statistics are used by the SQL Server query processor to estimate the size of intermediate results, and that has a large impact on the final query plan chosen by the query optimizer. So they're a crucial input to the query optimization process. You should manually update statistics on large fact tables after you switch partitions in or out of the fact table. You can use just update statistics table name to do this. This will update statistics using the default sampling strategy. These are typically just fine, but it's important to do this after each switch because you've changed a fairly large fraction of the data when you do that, and that can have a pretty significant impact on your query performance. It's particularly important for optimizing queries that read only the newest data. Now, it's very common to have a data warehouse where you've got several years of data, but the bulk of the queries are only querying the last few weeks of data. It's a very common scenario. If you switch in a new week every week, the system may not automatically update the statistics, and so you have no statistics on the latest week of data. So this is why we recommend that you update statistics after each partition switch operation. And in fact, after each nightly load, it's typically a good idea to update statistics with the default sampling, which is the standard that you get with update statistics. Now, note that statistics are maintained on the entire table, not on a per partition basis. As a result of that, it may take quite a bit of time to update statistics on a really, really big table. So you're going to need to budget time for that as part of your ETL process. To do a full database backup, you can back up to disk. Use backup compression to save storage. SQL Server 2008 has a new backup compression feature that both speeds up backups and restores and shrinks your backups by about a factor of 5 compared to uncompressed backups. So very, very useful feature. Speeds up backup and restore management operations and saves you a lot of resources in terms of space, either disk or tape space for backup. An alternative is to use a snapshot backup using a SAN. Now this can require more space and it requires this more expensive SAN hardware, but backup and restore can be made more or less instantaneous this way, and you can use the snapshot for other purposes, like testing or debugging. Piecemeal backup and restore is a very useful technique that you can use on large partition fact tables. The idea is that older historical partitions are not changing anymore, so we mark them read-only and just back them up once, and then you don't have to back them up on successive backups. The read-write file groups will be backed up each time we do a backup. And restore of read-only file groups can't be performed in parallel. That's something to know. There's a few key management features for SQL Server 2008 that I just wanted to call out again, if I haven't mentioned them already. Data compression is very, very useful for system management because it allows you to build a system with much less storage, and you can also get the working set for your data warehouse into memory with a lot less main memory. So it makes things a little bit easier in terms of designing your hardware configuration. Partition-aligned index views are another new feature of SQL Server 2008 that is useful for management. The basic idea here is that when you create, suppose you're about ready to switch a new partition into a fact table, and that fact table has an index view defined on it. SQL Server 2005, before you could do the switch, you would have had to drop the index view, then do the switch, and then rebuild the index view. Now, it can take a very, very long time to create a large summary aggregate on a really big fact table, a large index view. Because of that, dropping the index view was not a very pleasant thing to have to do because it means that you lost a lot of work. So partition-aligned index views, that feature is designed to eliminate this problem. The basic idea is that now you can create a staging table, create an index view in the staging table that has the same structure as the index view on the target fact table, and switch the staging table into the target fact table, and the index view associated with the staging table comes along for the ride, and it also automatically switches into the aligned indexed view on the fact table. So this could turn an ETL process that used to take hours into something that might only take minutes. The ETL, so another important management feature is a new extended minimal logging feature. So in SQL Server 2008, you can now use insert into select from with the table lock hint on the target table to bring data into a heap using minimal logging. So a heap is a table that has no indexes. Minimal logging is a type of logging where rather than logging old new value pairs for records in the log and then writing the data again to the database, we just log the extent allocations of the description of the new pages that we've allocated in the log, then write the data into the database directly, and then write a commit record into the log. So the bulk of the data the data only has to be written to disk one time in this case, rather than twice in the case with full logging. So this is typically very, very useful when you're loading, say, a fact table in a data warehouse. Now you can do this with insert into select from. And the nice thing about this is it allows you to create, it allows you to put the data exactly where you want it in terms of what file groups it goes on very easily. People before used to try to sort of work around this issue by using select into to load a staging table. The problem is that select into puts the target table on the default file group. And moreover, you can't specify any constraints on the target table or any indexes or anything. So it's pretty inflexible in terms of where the data goes and how it's structured. With insert into select from, you can create a table with exactly the constraints you want on just the right file group, and then load data into it with minimal logging. So this is an extremely powerful new feature for ETL. Minimal logging can be anywhere from 2 to 5 times faster than for loading data than the conventional full logging. Backup compression, as I mentioned before, is also very useful. It shrinks your backup time typically to be about 2.3 to 2.5 times it's a 2.3 times improvement in backup time typical. Also, your backups, again, will shrink to be about 1/5 of the original size. And finally, the resource governor feature is a very, very useful new feature, which I'll say a few words about later. So one common problem that we heard about in SQL when we asked customers about issues they had with SQL Server 2005 was the issue of runaway queries. So in some cases, customers would have a problem where a query would come in and use up a lot of resources like memory and CPU and keep them for a long time and essentially deny access to those resources to other users of the system. So in order to limit the scope of this type of problem, it's important to have some way to control the amount of resources that are allocated to different users or categories of work. So that's exactly what the resource governor feature is. It allows you to manage CPU and memory resources within a single SQL Server instance. This is for the relational instance. This is for a relational SQL Server only, and that doesn't work with analysis services at this point. So again, the goals were to help protect from runaway queries, also to ensure that there were adequate resources for mission-critical workloads or very important portions of a workload. For example, you might have an ETL job that just absolutely must run within a 1-hour window at night. You could reserve resources for that job using this resource governor feature that we've added in SQL Server 2003. The way it works is that there's 3 major concepts. There are workload groups. Okay, a group is a group of a group is a collection of queries, or it's really a collection of different connections to the database, and it can have associated with it certain criteria like how important the group is, the maximum memory for a single request, maximum CPU consumption for a single request, the timeout when a query is waiting for resources and when the query is in that group, maximum number of requests, and so forth. So each group is associated with a pool, which is a pool of resources, both memory and CPU. And there's a classification function that you define which categorizes connections into groups. So you can look at certain properties of a connection, like its IP address, the user that's logged in, the application name, the application role, etc., and use that to, again, classify that work for that connection into a specific group. One important task that a production support DBA is often asked to do is to tune the performance of the system during normal daily operation, and that involves figuring out what queries are taking the most time. So in the past, this has been somewhat of a difficult question to answer. What is taking the most time? But there's some new features in SQL Server 2008 that makes this quite a bit easier. So we have a new query and query plan fingerprint capability that's part of the plan cache dynamic management views. So there's a dynamic management view called DM exec query stats. This has new columns now, which has these plan and query fingerprints as part of it. So a query fingerprint is a unique, well, it's basically like a hash key that is almost guaranteed to be unique for a specific query. A query fingerprint is, however, general in that it's not dependent on the literals that appear in the query. So you suppose you have the same ad hoc query that occurs with, has exactly the same structure. You got two different versions of it with different sets of literals in the query, like different numbers or character strings or dates. Those two queries would both have the same query fingerprint. There's also a query plan fingerprint, which groups together all queries that have the same query plan. A typical way you might use this, you could use a query that's shown in the slide to find the top queries based on average CPU time. So these are the top query templates. So if you had two queries that were the same except the literals were different, they would be grouped together as one. They'd have the same query fingerprint. So this query can tell me what queries are taking the most time. Very useful, especially if you've got an ad hoc query workload. If you have a report writer or report application that's generating queries that are the same except the literals are different, this allows you to group them together. Just to summarize what we've talked about today, this has been a session about how to effectively manage your SQL Server 2008 data warehouse. And we talked about best practices for logical schema design, that we recommend using a star schema, choosing your hardware, both your CPU and memory system and your I/O system, how to do an initial data load, physical database design. So once you've picked your logical database design, how should you design your partitioning scheme, your indexes, and so forth, both clustered and non-clustered indexes, how to tune queries so they run efficiently, how to do incremental loads and unloads in partition tables, and how to effectively monitor and manage your system. And we also mentioned some of the enabling features in SQL Server 2008 that make it easier to manage your system. So at this point, you can submit your questions, and we'll respond to your questions. All right, Alex, I'm turning it over to you.
Thanks, Eric. Again, if you do have any questions for our presenter, go ahead and submit those now by using the Q&A pane in the lower right corner of your interface, and we'll be getting those in just a minute. You should all be seeing a survey now in your slide area. If you could take a moment to fill it out before you log off, we do appreciate any feedback you leave for us. All you need to do is follow the links provided to complete the evaluation. And looking at the Q&A, it looks like we have a question here. If you start off your data warehouse in SQL 2005 over the next few months, then how hard would it be to upgrade to SQL 2008 when it RTMs? Eric, could you answer that?
Okay. Yeah, that's a great question. So we've done a lot of work to make sure that SQL Server 2008 is upward compatible with SQL Server 2005. So it should be very straightforward to do that. It should just be a simple matter of attaching the database and going. Now, if you got a large data warehouse, then we do recommend that you consider using compression. So the compression feature does require some changes. You'll need to rebuild your index or structures with compression enabled. But again, once that's done, that's all you got to do. You don't have to change your application in any way.
And it looks like that wraps up the questions. Once again, I'd like to remind everyone to take one moment to fill out the survey prior to exiting the session room. And with that, I'd like to extend a special thanks to Eric Hanson for today's presentation. Thank you all for joining us today. You may now disconnect from the audio portion of today's conference.